At the peak, at this pages further on page 101 is the map of the lambda marker. This top band is 23,000 base pairs. That's the highest molecular weight marker we've had so far, so 23,000. The next one is 9,416, and then 6557, and then 4361. And then 2322, and 2027. In the note, it says that there are also two other bands. There's a 564 and a 125. The 125 you won't see, but I can distinctly see the 564 right there. Okay. And if you kind of go across your 100 base pair ladder, you can see that 564 is in the right place. I don't know if you can see it on the overhead, but you might be able to see it on your belt. Okay, so that's the Lambda Hindi 3 ladder. And the reason we're running Lambda Hindi 3 is it's got this huge band at 23 kilobases that we want to use to compare to our mouse genomic DNA. The next line is your undiluted mouse, and then your diluted mouse. Remember that we did dilution. You can see now why we did the dilution, because the undiluted is kind of a mess because the gel is overloaded, and so you have all this streakiness. If you look at your diluted, you can see this nice band. Now, why would genomic DNA give you a nice band? Remember, our work here was to try to isolate various gel, and agarose gel is completely incapable of separating fragments of that size. So that's why we get a single band, because all your really big genomic fragments are running in the same place on the agarose gel. Importantly, they're running up here in the neighborhood of the 23 kb band, or maybe a little higher. These gels will not separate DNA above about 20 kilobases, and so they look like they're running in the same place as the 23 kb band, maybe a little bit higher. But these gels just can't do that. So we can tell that the DNA is at least, say, 23 kb. We can't tell if it's actually 100 or 150 kb using this kind of gel. It's just a limitation of standard agarose gel electrophoresis. This was a 1% gel. We could run this gel at 0.7. That's about as low as you can go and still have the gel hold together. So we could have run a 0.7% gel, but I'm here to tell you that it wouldn't have looked any better. It wouldn't give us any more separation than we're getting here for your genomic DNA. So how could you measure genomic DNA to see how big it is? And the answer is you'd have to run one of those fancy pulse field gels that I mentioned earlier. Pulse field gels, so that's write that on the board over there. Pulse field gel electrophoresis uses agarose gels, but in a really unique way. Now, I'm going to tell you about pulse field gels because it's interesting, and it's nice to know that this exists. Whether you actually would ever do one or not is doubtful. Most people just never do it. But the way it works is you have, instead of a regular gel box, the gels are about the same size as the ones you've been running, but the gel box is really different. There's, I'm going to oversimplify a little bit, but if this is your gel, load your DNA into the wells. I'm just going to do a few wells here. Your DNA, remember, is negatively charged. large, so we want the positive electrodes down here, and the positive electrodes down here, and the negative electrodes up here. And so there's one negative electrode over here, and another one over here. It's actually more electrodes than that, but let's keep it simple. Positive electrode here, positive electrode here. And these electrodes are oriented like that. Well, the electrodes are at an angle, so when you turn on the gel, what you're going to first do is a pulse this way, and your DNA will migrate like that, at an angle. And then you're going to pulse this way for an equal amount of time, and now it'll go this way. And then you pulse again that way. And then you pulse this way, and so on. And so your DNA works its way down the gel. Now, how does this enable you to separate really large fragments? Well, let's suppose that this fragment is 100 kb, and let's suppose this fragment is 200 kb. My arm's one fragment, this is another fragment. Now what happens, they're together, we turn on the current going this way first, and what's going to happen is, in order to move, they have to orient. They can't move through the gel like this, they're too big, that's why we get no separation, right? So what has to happen is they have to orient in the direction of the field vector, and then they can move. Okay, so these things have to reorient in order to move. We turn on the current for maybe a minute in this direction. This thing can orient maybe in 10 seconds, and then it's got 50 seconds to move. This one might take 50 seconds to orient, and then it's only got 10 seconds. Okay? So the big ones take longer to orient and therefore have less time to move. The smaller ones orient quicker and have more time to move. Okay? So that's the basis for being able to separate really big molecules. And these pulsed field gels can actually separate 100 kb from 110, from 130, from 140, up to actually hundreds of kilobases. So we actually have one of these, and we did experiments years ago where we used it a lot, not so much anymore, but it's an effective method for separating really big DNA in gels. This particular apparatus that we have is made by Bio-Rad, and it's called Chef gel for plant horizontal electric field. It's expensive because you have to have a power supply, you have to have this pulse controller that controls the pulses. The box itself is really big and complicated, and then they charge probably too much for it. So it's not cheap, and most people don't have them. So when we make genomic DNA that we want to be high molecular weight, we'll do this, and we'll look at it and go, okay, well that looks really good. It's probably big enough for our purposes, and if you're doing really high molecular weight DNA for a kind of sequencing we'll talk about later, then you'll find out when you do your sequencing run if it was big enough. If you have one of these chef gels, then you could actually move it in size. Okay, does that make sense? Any questions about the chef gels or the pulse field electrophoresis gels? There were various configurations of these things made. They were hot for a while. A couple of companies made them. I think Bio-Rad makes the only one now, because people mostly don't do it. Okay, so your DNA looks great. It's the best we can do for seeing if it's high molecular weight without running chef gels. Okay, so this was your undiluted and your diluted. This is some DNA that we gave you. You can see your DNA actually looks a little better than ours. Ours has been sitting around for a while. Then you've got another lambda marker here. And now this part of the gel is the part of the gel where we're looking at your PCR product from the TTR amplification. Remember, we were trying to amplify one 1100 base pair gene sequence from the entire 3 billion base pair mouse genome. Anyway, 100 base pair ladder. We're expecting a band at 1100 base pairs. This is 1000, that's 1200. This is in exactly the right place. So we believe you have successfully amplified a single copy gene, about a 1100 base pair sequence from the entire genome. So, and you know, maybe there's a faint off-target band here, but think about those 2 short primers going into this 3 billion base pair genome, finding your one sequence and then amplifying it. That's pretty remarkable. And to do it with really great specificity. It's possible there's a minor off-target product here, maybe another one there. But with total genomic DNA, that's not surprising because there's 3 billion base pairs of sequence, right? So that looks really good, looks great. This was your 1 microliter sample, and this was your 5 microliter sample. That's why in the 5 microliter sample, maybe you see these minor off-target products and not in this one. But really, this is a really tiny portion of your DNA. If you wanted to verify, and you should, that this is actually the TTR gene sequence, and that you amplified TTR, you should sequence this. We're not going to because we already sequenced the TTR, our TTCR product. But in your own research, you should probably sequence that to make sure that you amplified the right thing. Okay? Before you go ahead and do more experiments with it. All right, so another successful gel, yes?
There's bands at the very top of the wells.
Oh. This is DNA that gets stuck in the wells and has a hard time getting out. So when you've got total genomic DNA like this, you've got some really big DNA, and remember, not all of it, we tried to get it into solution completely by rocking for 6 days or whatever it was, but there's probably some that's still not completely in solution, and that's going to stick up at the top of the wells. It'll stain with your DNA stain, but it's not migrating into the gel. Okay? With high molecular weight DNA, you'll often do that.
Is it reasonable to extract the DNA from the banks from the gel?
Yeah, so if you do a genomic PCR and you really want this fragment, but you get an off-target product somewhere else, you can actually cut this out of the gel and then purify the DNA out of the gel. Biolabs has a kit for doing that. Other companies do as well. When you do that, recovery from bands on a gel has been driving people crazy ever since molecular biology first started, right? And there have been all kinds of crazy methods developed. But basically what you do now is you cut out the band and melt the agarose, and then there's an extraction method for getting the DNA out. Don't expect that you're going to get 100% recovery. You will not. But you can get enough then to continue on with your experiment. If you have this band and an off-target product, and you try to sequence it, that's not going to work. You're not going to be able to sequence 2 things simultaneously and get anything reasonable. So in that case, you would need to gel purify this band before sequencing. I mean, we do have this little bit of off-target, but this is not enough to cause a problem for sequencing. It would have to be a more substantial band than that. If you ran your PCR product and you had this band and then another band that was really clear and visible, then you need to gel purify before sequencing.
What is the streak in length?
Oh, the streak? When you have an overloaded lane, you always see the streakiness. It's just completely overloaded. And so you always see this kind of a streaky situation. You'll notice in this one where it's not overloaded, you don't see that at all. Okay? Okay, another great result, really good.